So what we're doing now is we are writing the equation for situations. We're basically writing the function rule. And what that means then is we will be able to say if we wanted to calculate for a certain variable, what would the other variable be? And that's essentially what equations do. Equations can tell you what the other matching variable value will be when you choose one of the values and say, I want you to calculate for that, okay? And this situation looks like this, okay? Here's a rule. You can estimate the temperature of the environment by counting the number of chirps of the snowy tree cricket, okay? This cricket chirps faster or slower depending on the temperature. And the outdoor temperature is about 40 degrees more than 1/4 of the number of chirps that the cricket makes in a minute. So if you can count the number of chirps that a cricket makes in a minute and take 1/4 of that, 40 more than that is going to be what the temperature is. This is a pretty direct relationship, pretty neat. Okay, what is the function rule that represents this situation? One thing that you can do is you can model this, or you can visualize it by saying, okay, this total temperature here is going to be 1/4 of whatever the number of chirps is, and then you add another 40 on because you always have to go up by 40 in order to hit the right temperature based on the number of chirps. So what does that look like? Okay. The temperature is 40 more than, and remember with 40 more than, we're going to have a plus 40. 40 more than 1/4 of this thing that varies. The number of chirps that the cricket makes in a minute varies, right? And so that's a variable value that we're going to call n. And you take 1/4 of that number, add 40, and you'll know what the temperature is, okay? So this is the function rule. Temperature is equal to 40 more than 1/4 the number of chirps. Got it? Okay, so you're going to try and do that with this situation right here. Okay, a landfill has 50,000 tons of waste in it, and then each month it accumulates this many more tons. So you're going to say the total amount of waste in tons based on the number of months. So you're comparing the months to the total waste. And just like up here, you have this set amount that's added and then some thing that multiplies the variable amount. You're going to figure out what way to set that up. Now, based on that last example and on this example, you can see that we're writing rules for real life situations. And when we do that, the reason that we do that is because we have to decide what the equation is based on what's going on in real life. Now, this is kind of small, but you can see here that it says the reserved seating is $25 per seat. There's 10 rows, each with 12 seats. Now, up here, the general admission is $10 for each seat. There's 30 rows, each one with 16, okay? And a concert seating plan is that I just described. And reserved seating is sold out. So we already know we got all the money that we can make from this, okay? There's 10 rows of 12, and each of those seats got $25. So that is going to be a set amount. We already know that that amount came in, and that's going to be added to the end to find out what the total amount of money we'll bring in is, okay? So write a function rule to represent the total revenue from ticket sales, which depends on the number of these general seating tickets sold, $10 each. Okay, write a rule, and then what's the maximum possible revenue? Because we can't go up forever. There's a limit to the number of people that will sit in this venue. Okay, so here's what it looks like. Total revenue, which we define, when we define the variables, we say let R be the revenue, total revenue. Okay, it's equal to the general seating revenue. We're going to multiply the ticket price by the number of tickets. That's a very standard thing. Number of items sold times their cost for each one. Okay, and plus we're going to add on that money that we brought in from the reserved seating. Okay, so N is the number of general seating tickets sold. That's the only thing that's going to vary in this situation since these seats are sold already. So we say R, the total revenue, is equal to 10 times the number of general admission tickets sold, plus we got $25 times 10 rows times 12 seats per row, okay? And when we do that, you see that this is equal to 3,000. So we've got, as a rule, the revenue is going to be 10 times the number of general seating tickets plus that 3,000 that got brought in from reserved seating. So the function rule represents the situation. And because we calculate here, there are 30 rows of 16, there are 30 rows times 16, or 480 general seating tickets available to be sold. So if we substitute that into the equation, we find out that 10 times 480 is $4,800 that could come from here. That 4,800 plus this 3,000 from the reserved is 7,800. That's the maximum they could sell. That'll sell it out. So the maximum amount that they could bring in is $7,800. You're going to try this right here, and they add an additional question here that's interesting, which once they set up the situation, they say, what if you modified the situation? Does it give you half as much if you stay for half as long? And you'll have to read that to see. Okay, just a little note here. In the next slide, it's about 6 minutes long, and it's a whole bunch of example problems. You're free to skip over it, but it might actually be really helpful for you to watch. Up to you. So because there were only 2 example problems that we wanted to show you, and you maybe do need some more experience at this, I wanted to include some of the book problems. In fact, these are problems that if you go to the resource page, this was an assignment that we normally do. Now we're using Math Excel. So there are videos showing how to solve each one of these if you go to the resource page, okay? But I'm gonna just show you the answers really quickly here. And I wanna point something out. Mr. Lakai made the good point that a lot of you are familiar with y equals mx plus b, okay? Where we're gonna need this when we, later on, when we start to learn slope-intercept form, and many of you already know it, y equals mx plus b. And essentially what you have here is you have this set amount, okay, and then some multiplier on the variable. And in this case, you see 5 less than means that's going to say minus 5. And 5 less than what? The product of 4 and x. So x is here, and it's 4 times x, right? And that's what y is equal to. Y equals mx plus b. And we can use this to graph. Essentially, if x was 0, we'd have 0 times this amount, and 0 of the variable would give us just this amount, okay? Now, let me erase this, and I'm going to show you our answers for all of these and just talk you through them real quick. Okay, so what we have here is this, okay? 5 less than the product of 4 and x is y. That's what this says. Or y is, when you see y is, that means where is appears will be the equals. So y equals 5 less than the product of 4 and x. C is, or C equals 8 more than what? Half of n. Got it? Okay, is A, so that means A is equal to 7 less than 3/5 of B. So we take 3/5 of B and we go 7 less than that. Here we see is W, that means W equals, and what is it? It's 2.5 more than this quotient. We have to take the quotient first of H and 3. Remember, whatever comes first goes on top. And we want 2.5 more than that, okay? Those are those. Now here, these are real life situations. A worker's earnings, E, are a function of the number of hours worked. N is the number of hours worked, and that person makes $8.75 an hour, so $8.75 times each hour that they work will be E, their earnings. Here, pizza, price of a pizza is the base price of $6.95, so you see that appearing at the end. And then 95 cents for each topping T, so you multiply the number of toppings you got times 95, and you add that to the base price of the pizza, $6.95. Together it will be P, the price of the pizza. Okay. Here this says the wheelbarrow holds some n number of 4-pound bricks. So the total load of the wheelbarrow is the sum of its 42-pound weight. That's going to be plus 42 no matter how many bricks are in there. And then 4 times each brick, however many bricks are in there. That would be the total weight or load. Here, almond extract is being used up. So what's remaining is 8-ounce bottle minus however many 1/6 ounce groups that we used for each one for a batch of cookies. So take away 1/6 for each, or 1/6 of an ounce for each batch from that 8 that's in the bottle, and you'll find the almond extract remaining. These three actually give you the situation and then you solve it. So here you got the helicopter hovers 40 feet above the ground. We're starting at plus 40. And then we say it goes up or climbs positive 21 feet times the number of seconds, which t represents the number of seconds. Okay, so this is the rule. The height is 21 times the number of seconds plus that initial 40 feet up it was, and they want us to then calculate it for after 45 seconds. So when we put 45 in there, we find out that after 45 seconds, going up at 21 feet per second, starting at 40, would be 985 feet above the ground. For this one, divers are diving at a rate of 50 feet a minute, so negative, because since they're going down, times t, the number of minutes, but they already started at 10 feet below the surface of the water, so this is minus 10 at the start, and then take away 50 feet for every minute. They want us to calculate it for 3 minutes, so negative 50 times 3 is negative 150. Take away another 10, because we were already down 10, negative 160 feet below the surface. And finally, you're publishing a book. You have 24 pages of introduction, so that's plus 24. You have 48 more pages at the end, that's plus 48, and then 12 page chapters. So 12 times however many chapters there are. Okay, you could actually combine this to 72 if you like at the start, because that's a set number. 24 at the start and 48 at the end will be 72 no matter how many chapters there are, but each chapter has 12 pages. So you do 12 times the number of chapters, and then they say, calculate it for 25 chapters. So 12 times 25 is 300, plus the 24 at the start and 48 at the end would be a total of 372 pages. Yep, and we'll be able to graph these eventually. That's how you do these. All right, hopefully you made sense of that. You can try these lesson check problems. We've left out problem 4 and problem 7, so just try these that are here. Good luck with this.